APAB Calc, and we're doing 2.4, which is the chain rule. So up until now, I've had to really carefully select problems so that you wouldn't have to use the chain rule because, to be honest, most differentiation that we're going to see moving forward uses the chain rule. Essentially, you have to use the chain rule anytime there is a function inside another function, and I'll show you what I mean by that in a second. If you want to differentiate a function in a function, you have to use the chain rule. So for example, if I gave you y equals x squared plus 3, there's only this one function, x squared plus 3. It's not inside another function. That would not be an example of a chain rule problem. You could just differentiate. But if I gave you y equals the square root of the quantity x squared plus 3, because the x squared plus 3 is a function inside another kind of function, inside a square root, it would be a chain rule problem. Most of the problems we're going to see moving forward are some kind of chain rule problem. Not all of them, but a lot of them. So on page 131, your textbook kind of writes a version of the chain rule. The hardest part for me with the chain rule is that there's no really good way to write the chain rule, because a chain could have two functions, like the one you see here, or I could make you have a chain that has three different functions, like a function inside a function inside a function, and that's going to look a little bit different. So we're going to walk through the way that the book defines it, and then we're just going to do a lot of examples, because honestly, with the chain rule, the best thing you can do is start practicing. Again, the chain rule is going to be a thing that you're going to see a lot of, and you're never really going to be expressly asked to use the chain rule. You're just going to be asked to differentiate a function that has functions inside other functions, and you're going to need the chain rule. So according to page 131, this is their notation, right? So let y equal f of u, where u is also a function of x. So u is g of x. Basically what they're saying is y equals f of g of x, which is composition of functions from algebra 2, where g is the function that is inside the f function. Dy dx, meaning the derivative of y with respect to x, is dy du, meaning the derivative of the y function, where you just differentiate the outside function exactly as it is and leave the stuff on the inside the same. So the derivative of the y function with respect to u times the derivative of the x function. So another way to write that is if you have f outside g, it would be the derivative of the f function, but you don't change the g of x at all, times the derivative of the g function. So derivative of the outside function, and you don't change the inside stuff at all, times the derivative of the inside function. So we're going to walk through this. A little bit in some examples, and I think it'll make a little bit more sense. There's also a lot of good chain rule videos on the interwebs, so if you want extra practice at this, you can definitely find it on Khan Academy, like you can find most places. All right, cool. So let's do some practice with the chain rule. All right, so example 1. Okay, we're gonna find y prime, and I'm gonna give you a couple of these to try. So let's do y equals sine of 2x. Let's do y equals x squared plus 1 to the 4th. And let's do y equals, let's do a square root of 3x plus 2. Okay, cool. So we're going to walk through these three first, and then we'll get to progressively harder examples. Again, the trick here is to recognize that there is a function inside another function, right? So the inside function is usually the function that has the x. So I'm going to color code a little bit and say, oh, look, the inside function is the 2x, which makes the outside function sine of stuff, right? So when I want to find my y prime, right, my y prime is going to be the derivative of the outside, which I sometimes just write as d out. So the derivative of sine, well, the derivative of sine is cosine, and I'm not changing the 2x on the inside, so there's the derivative of the outside function, right, times the derivative of the inside function, which would just be a 2, right? The derivative of 2x is just a 2. So my final answer for A is going to be 2 cosine of 2x, and the 2x stays inside the cosine, okay? So when we look at B, right, and let me do some nice little lines to make this a little bit easier. So and I'm just going to put an arrow to make it clear that that wasn't equal. So when I look at B, now there is an interesting option here. Somebody might say, oh, well, what if I just wanted to FOIL this entire mess out? And I guess you could. You could use Pascal's triangle. It would be awful. So the inside function here is the x squared plus 1, and the outside function is stuff to the 4th, okay? So when I want to find my y prime, right, when I want to find my y prime, the derivative of the outside function times the derivative of the inside function, right? So my derivative of the outside function, my outside function is stuff to the fourth, right? Sorry, computer fell asleep. My outside function is stuff to the fourth. So the derivative of stuff to the fourth is 4 stuff to the third, right? That's just a power rule, right? And that stuff on the inside is an x squared plus 1 times the derivative of the inside, which is going to be a 2x, right? 2x plus 0 if you wanted to worry about that plus 1 for the constant. So when I clean this up, I'm probably going to write this as an 8x in front of this x squared plus 1 quantity cubed, right? That's the way I'm going to write that. Now, before I do c, it's helpful to recognize that c is a little easier if I rewrite the root as a 1/2 exponent, okay? So I'm going to use this, right? The inside function is the 3x plus 2, right? And the outside function is that stuff to the 1/2, right? So when I differentiate, right, my derivative of the outside, d out, times d in, right? So d out times d in is not a mathy thing, it's just an easy way for me to write it, okay? So the derivative of the outside is going to be, drop the 1/2 down in front, so 1/2 stuff to the negative 1/2, right? And that stuff would be a 3x plus 2, because I'm not changing it, right? I'm not changing the inside stuff, times the derivative of the inside, which is going to be a 3. So chances are, when I rewrite this, I get a 3/2 times this whole thing, 3x plus 2 to the negative 1/2, or, so that answer's fine, or I could rewrite that, putting that stuff on the bottom, and make this a 3 times a 2 with that whole quantity to the 1/2 on the bottom, or I could write it with that as a root on the bottom. Any of those would be fine, right? And I don't care so much about which of those answers you end up with, I just care more that you're able to do the chain rule. So what we're going to do is I'm going to erase E1 and give you a P1, same basic thing, right? I'm just going to change what those 3 functions are, and then you're going to give it a try, okay? And you can pause me if you want. It is helpful to be able to identify which function's the inside function and which function's the outside function. I will say that's kind of a big deal. So once I write those problems, if you want to pause me, you can, and then I'm going to work through them. So once you unpause me, we can go over stuff together. Of course, the downside to me erasing those in advance is that then I forget exactly what I made my stuff. So let's do a tangent of a 5x. Let's do a 2x cubed plus 4 to the 6th, sure. And let's do the cube root of a 6x plus 1. Great. Okay, so try and find y prime. Go ahead and pause me if you want, okay? So my inside function, I'm actually going to be lazy and just label the inside function on all of these real quick, because that way I can use the orange marker all at the same time, okay? My outside function is going to be, in this case, tangent, right? In this case, my outside function is the stuff to the 6th, right? And in this case, my outside function is the cube root, right? Which I guess I should probably make a note down here that this is actually a 6x plus 1 to the 1/3, right? So the 1/3 power is the outside function. So we go ahead and walk through A. For A, my y prime is going to be the derivative of tangent, right? Because tangent's my outside function, times the derivative of the inside function, which is a 5x. So the derivative of tangent is secant squared of whatever was inside the tangent, right? And that's one of your note cards. You do want to practice that, right? And then the derivative of 5x is a 5. So the way you're probably going to see that answer is as a 5 secant squared of 5x, right? For the next one, right, again, my derivative of the outside times the derivative of the inside. Well, the derivative of the outside, since it's stuff to the 6th power, right, like parentheses 6, is going to be 6 stuff to the 5th. And I keep the stuff the same. It's going to be that 2x cubed plus 4, right? And then the derivative of the stuff is going to be, the derivative of this inside would be a 6x squared. So I'm pretty sure that this answer is going to end up looking like a 36x squared times 2x cubed plus 4 all to the 5th, right? Now for this one, for the last one, right, I'm going to drop this 1/3 down in front. It'll be the stuff to the negative 2/3, right, because it would be 1/3 minus 1, right? So with this 6x plus 1 on the inside, and then I'm going to times that by the derivative of the 6x plus 1, which would just be a 6. So when I clean this up, I end up with a 2 in front of this 6x plus 1 to the negative 2/3, and that answer's okay. You might also see that with the 6x plus 1 to the 2/3 on the bottom. It is unlikely, but not wrong, that you would see this as a cube root with a squared, right? So the cube root of 6x plus 1 quantity squared. That's unlikely, but it's correct, right? So that's our E1 and P1, and we'll stop this video here, and then we'll give you some more in the next video.